All right, if you're writing Go, you're almost certainly using Goroutines. But let's be honest, managing them can get complicated fast. So today we're going to build a kind of mental toolbox. We're going to demystify the core concurrency tools in Go's sync package. By the end of this, you'll have a much clearer idea of exactly which tool to grab for which job and why. Sound good? Let's dive in. So here's our game plan. We'll start with the workhorse, sync.WaitGroup. Then we'll look at a really specialized tool, sync.Once. After that, we'll get into some more advanced stuff with sync.Cond and finish up with the performance booster, sync.Pool. And of course, we'll wrap it all up with a cheat sheet you can take with you.
All right, first up, the wait group. This is probably the tool you're going to reach for most often. It's really the bread and butter of Go concurrency. Its job sounds simple, but it's absolutely critical. It lets your main program wait until a whole bunch of Go routines have finished their work.
You know, the best way to think about this is with a simple analogy. Imagine you're hosting a party, right? And you send, say, 3 of your friends out on errands. One to get ice, one to get snacks. You get the idea. The wait group is basically your mental checklist. You know you're waiting for 3 people. You can't start the main event until all 3 are back. As each friend returns, you tick them off the list. Once the list is empty, boom, party time. That's all a wait group is doing.
Okay, so how does that party host checklist translate into actual code? Well, it boils down to just 3 methods. First, there's add. You call add with a number, like wg.add3, to tell the wait group, hey, I'm waiting for 3 things to happen. Then, inside each Go routine, when it's finished its job, it calls done. That's your friend coming back and saying, I'm done, which ticks the counter down by 1. And finally, back in your main function, you call wait. And this is the cool part. Your program just pauses. It literally stops and waits right there until that counter hits 0.
Let's look at a classic example right here. You can see we have a for loop spinning up a bunch of worker Go routines. Now notice the pattern. First, outside the Go routine, we call wg.add, 1. We increment the counter. Then we launch the Go routine. Inside it, the very first thing we do is defer wg.done. Using defer is a fantastic habit because it guarantees that done will be called no matter what right before the function exits. And then at the very end, outside the loop, wg.wait just sits there patiently until all those workers have called done.
Okay, this is super important. A classic rookie mistake, and it can cause some really nasty bugs. Look at the wrong example. The wg.add is inside the new Go routine. Why is this so bad? Well, it's a race condition. There's no guarantee that the new Go routine will even start and call add before your main function plows ahead and hits wg.wait. If the counter is still 0 when wait is called, your program just exits immediately and the work never gets done. So the rule is simple and you should never break it. Increment the counter before you launch the Go routine. Now for a couple of pro tips that'll make you look like a seasoned Go developer. First, you always pass a wait group by pointer. See the little asterisk there? That's not optional. Why? Because if you pass it by value, Go just makes a copy. The Go routine gets its own private copy of the wait group. When it calls done, it's decrementing its own counter, not the one your main function is waiting on. The result? Your program just hangs forever, a deadlock. And second, I'm going to say it again because it's that important, always use defer wg.done. It's just the safest, most foolproof way to write this code.
Okay, let's switch gears. Our next tool is sync.Once. Now, unlike WaitGroup, this one is highly specialized. It's not a Swiss Army knife, it's more like a scalpel. It has one and only one job: to make absolutely sure that a particular piece of code runs exactly once, and I mean exactly once, even if 1,000 Go routines are all trying to run it at the same time.
And the perfect analogy for this is a grand opening ribbon-cutting ceremony. You could have 10 different people, all lined up with scissors, all rushing to be the one who cuts the ribbon. But only one person can be the first. Once that ribbon is cut, it's cut. The other 9 people can snip all they want, but the action is already done. Sync.Once is that ceremony official who ensures the ribbon is only truly cut one time.
So where do you actually use this? The number one use case by far is something called lazy initialization. This just means we don't set something up until the very first time we need it. Think about establishing a database connection. That can be a slow, expensive operation. You don't want to do it unless you have to. By wrapping that connection logic inside a function and passing it to onceDo, you get a guarantee. The very first Go routine that needs the database will create the connection. Every other Go routine that comes after will just get to use the connection that's already there. It's clean, efficient, and thread-safe.
So, let's nail this down. The key takeaway for sync.Once is simple.
It guarantees a function runs just one time, even under heavy concurrency. Its main job is that lazy initialization we just talked about, especially for things like singletons. And honestly, it's just a much safer and more readable way to do this than messing around with your own mutex and a did I do it yet Boolean flag. Let Go's standard library handle that complexity for you.
Okay, time to level up a bit. Our next tool, sync.Cond, which stands for condition variable, is definitely more advanced. You won't need this every day. This is the tool you pull out when your Goroutines need to wait for something more complicated than just other tasks are done. They need to wait for a specific condition in your program state to become true.
Let's go with another analogy. Imagine a track meet. You've got a bunch of runners all crouched at the starting line. They're all waiting. They're not waiting for a countdown. They're waiting for a very specific condition. The track has to be clear, and the officials have to be ready. There's one official whose job it is to check that condition. Once everything is perfect, that official fires the starting pistol. That pistol shot is a signal, and all the runners take off at once. Your wait and go routines are the runners. The cond is the official with the starting pistol.
Now here's how it works under the hood. A cond is always paired with a mutex. You can't use one without the other. It's got three main operations. First, wait. This is what the runners do. A go routine calls wait and it goes to sleep. But, and this is the magic part, it automatically unlocks the mutex while it's sleeping, so other go routines can get in and change the state. Then you have signal. This is like tapping just one of the sleeping runners on the shoulder and saying, hey, wake up. Finally, there's broadcast. That's the starting pistol. It wakes up every single go routine that's currently waiting. Okay, listen up, because this is probably the single most important and most frequently misunderstood detail about sync.Cond. If you're ever in a Go interview, this question is almost guaranteed to come up. Why do you have to, and I mean it's not optional, why do you have to wrap the call to wait inside a for loop? And the answer is a strange-sounding term, spurious wake-ups. It turns out that sometimes, for reasons deep in the operating system scheduler, a waiting Go routine can just wake up on its own, randomly, even though nobody called signal or broadcast. It's weird, but it happens. So the for loop is your defense mechanism. When your Go routine wakes up, the first thing it does is recheck the condition in the loop. If it was a false alarm, a spurious wake-up, the condition will still be false and the loop will just call wait again, putting it right back to sleep. It ensures you never proceed unless the condition is truly met.
So to recap, sync.Cond. You use it for complex, state-based waiting. You must pair it with a mutex. And that for loop around the wait call, it's completely non-negotiable. One last piece of advice though. A lot of the time, especially for producer-consumer patterns, you can solve the same problem using Go's channels, and the channel-based solution is often clearer and more idiomatic. So always ask yourself first, can I do this more simply with a channel?
All right, on to our final tool, sync.Pool. And I want to be really clear about this one. This is not a synchronization tool like the others. You don't use it to coordinate Go routines. Sync.Pool is a pure performance optimization tool. Its one and only job is to help reduce the workload on Go's garbage collector. It does that by letting you reuse objects instead of creating new ones over and over again.
The perfect mental model for a pool is a stack of trays at a cafeteria. When you get in line, you don't expect them to forge a brand new tray just for you. That would be incredibly wasteful. Instead, you get a clean one from the stack. When you're finished with your meal, you put it on the return rack. It gets washed and put back on the stack for the next person. A sync.Pool does the exact same thing for objects in your code, saving the cost of constantly allocating and deallocating memory.
So, what's a good candidate for a pool? Think about things that are temporary and get created a lot, especially in high-traffic code. Things like byte buffers for network I/O, or maybe a big struct that you use for encoding and decoding JSON. And what's a bad candidate? Absolutely anything that holds a critical resource or needs to be closed properly. Never, ever put things like database connections or open file handles in a pool. The pool offers no guarantees about their life cycle, and that's a recipe for disaster.
There are a few hard and fast rules for using sync.Pool safely. First, remember its only purpose is to ease up on the garbage collector. It's not for anything else. Second, and this is the big one, a pool is just a cache. It's not permanent storage. The garbage collector can decide to empty the pool at any time without warning. So you can't rely on an object being there. Third, the API is super simple. You get an object and you put it back. And finally, number 4, when you get an object, you have to assume it's left over from a previous use. You must reset it to a clean state before you use it.
clear out that byte slice, zero out that struct.
Whew. Okay, that was a lot. But we've now filled up our toolbox. So let's do a quick recap with a handy cheat sheet to pull it all together.
Here it is, all in one place. Need to wait for a bunch of goroutines to finish? That's a job for sync.WaitGroup. Need to make sure an initialization function runs exactly one time? Grab sync.Once. Got a tricky situation where goroutines need to wait for a specific condition to be true? That's the advanced case for sync.Cond. And finally, if you've identified a performance bottleneck because you're creating too many temporary objects, sync.Pool can help reduce that GC pressure.
And there you have it. These 4 tools are fundamental to writing solid, high-performance concurrent code in Go. They're not interchangeable. Each one is designed to solve a very specific kind of problem. Getting comfortable with them is what separates good Go code from great Go code. So, now that you've got the toolbox, the real question is, what are you going to go build with it?